if you turn this video at one point off and tell me what the reason was, please, so that I can improve. Otherwise, I'm trying to learn electrical engineering to the electrochemical equivalent, and after we've done that, we're going to do standing yoga. And if you participate in the standing yoga, then it's wird ja anders. Electrochemical equivalence. It may have occurred to you when we discussed the copper voltmeter that there is really no practical purpose in depositing copper on copper by electrolysis. So I was wondering a bit why having a spoon with out of copper with a copper layer. So the idea was, we're having a setup, we're having a copper liquid something, we're having a copper block and our copper spoon. Now we're putting the anode here and the cathode here. The current goes from here and it takes copper from the copper block, puts it into the copper liquid, and here some copper of a copper liquid comes onto a copper spoon. And now we're having a copper spoon with a copper liquid. It makes more sense to have a nickel spoon with a silver liquid, silver blade or whatever. Something like that. Okay, of course any electroplating process does involve putting a metal onto the same metal to build up a coating of suitable thickness once the first layer of metal particles has been deposited on the article to be plated. Did we just say that it's necessary to do that? Of course, any electroplating process does involve putting a metal onto the same metal to build up a coating of suitable thickness once the first layer of metal particles has been deposited on the article to be plated. Let's do it. I don't understand it, but I think we're going to understand it from the context. However, a copper voltmeter is rather a useful laboratory device because there is little difficulty in obtaining a hard, even coating of copper deposited under a wide range of conditions. A hard, even is a verb. What is it? It is even. It all the places the same. Because there is little difficulty in obtaining a hard, even coating of copper deposited under a wide range of conditions. Okay, we're saying it's easy to make copper onto something. You should set up a copper voltmeter using the circuit shown. We need the copper anode and the copper cathode. I don't have my open. The rheostat should be adjusted so that when the switch is closed, a current of between 0.5 and 1 ampere flows. The cathode should then be removed and cleaned in the following manner. Okay, we have our copper anode and our copper cathode. The current comes and then it goes through something and there's somewhere a switch. Now we should now clean first we should make it dirty, now should we clean it? No, the first thing, the cathode is first rinsed in water to remove copper sulfate solution and dried with a clean cloth. Okay, we're taking our cathode, we are rinsing it with water, that removes the copper sulfate, and then you should dry it with a clean cloth. The surface of the cathode is then cleaned with fine earthy paper to produce a polished metal surface which should not be then touched by your fingers. We need an emery paper, whatever that is. We need something to clean it, and while we're doing it, we should not hold it in our hands. Third, the cathode is rinsed in clean water to remove copper dust. And we should rinse it again, because there's now copper dust on it after we have polished it. A further rinsing in methylated spirit is now required to remove water. Spirit is hygroscopic and any grease on the surface. I don't know what the grease is. I don't know what metaphoric spirit is. And I don't know what hygroscopic is. A further rinsing in methylated spirit, I think that it's some type of liquid, is now required to remove water. Spirit is hygroscopic and any grease on the surface. I don't know what grease means. Okay, whatever, we should clean it again. Fifth, The cathode will dry quickly, especially if held in a stream of warm air well above a small Bunsen burner flame and is then weighed. Is it necessary to let it dry quickly? Don't we have some minutes time left? Whatever, we can let it dry faster, and if you want, we can take a 1000 degrees Bunsen burner fire. The cathode can now be put back into the voltmeter. What did we want from it? Let's do that. The time at which the current is switched on should be noted. Okay? And eventually the time at which the current is switched off. Okay, we're having taken our cathode out of it. Or didn't we even start it in the first place? I think we didn't start it. We just have made our cathode very clean, I think. So we took our cathode, made it very clean, poured it in, noting the time when we're starting the switch. And when we're making it off again. The period of time required to plate the cathode adequately is about half an hour. That is why we needed to hurry with the drying process, because we needed half an hour for the whole other thing. The ammeter reading should be noted at 5-minute intervals so as to obtain an average value of the current flowing. Okay, over this half hour, our very clean cathode, whatever it was, is in it. Half an hour. We are stopping the time, half an hour. And every 5 minutes, we should look how much current is flowing. And why did this in there? It is plated with something. The copper the copper deposited on the cathode will be found to be pink in color, and when removed from the voltmeter should be rinsed in water, in spirit, dried, and then reweighted. Okay, we have our cathode, which has turned pink through the copper on it, which had gotten onto it in the past half hour, which we should stop and every 5 minutes check how much voltage is still running there, what it was. Now we should clean the whole thing again. It will help to consider some specimen results for such an experiment. Original weight of clean cathode 57 gram. Time current was started at 10:45 a.m. Ammeter reading at 5-minute intervals 0999, 098, 097, 099, 101 ampere. Average value of current 0.99 ampere. Okay, it got a bit down and went up again. I think we're gonna point to that in a moment. Time current was stopped at 11:15, exactly 30 minutes. Final weight of cathode 57.93. So it was in the beginning 57.34, so it got 0.6 gram heavier. Weight of copper deposited 0.6 gram. Time for which current flowed 1800 seconds, half an hour. From these experimental observations, a calculation can now be made. Number of columns of charge passing through the voltmeter is 1800, that is RV seconds, times 0.99 columns. We measured on average 0.99 ampere, so that is what we got there. An example, RVs 1798 columns. That fits. Okay, we had put through the voltmeter past 1789 columns of current. Mass of copper deposited by 1 column of charge is 0.6 gram divided by 1782. These are 0.00033 gram. We're saying that 1 column of current has brought 0.00033 gram of copper onto our cathode. We have arrived at a final result that the mass of copper deposited by 1 column of electricity during electrolysis is 0.00033 gram. You will notice that an assumption has been made in this calculation. No? That is that each column of electricity deposits, the same mass of copper. We said that 1 column transports 0.00033 gram. What if 1 column was better than the other one? Although this may seem to be a reasonable assumption, nevertheless, as scientists must always obtain experimental evidence to confirm any hypothesis he or she puts forward. It should be obvious that the above experiment can be repeated many times using different currents and different lengths of time. In fact, this may well be the case if various groups of pupils perform such an experiment at the same time in your school laboratory. In fact, they will all arrive at the same numerical result, within the limits of experimental errors, no matter how often the experiment is performed. Such a piece of factual information, which is obtained every time an experiment is performed, is what is termed a scientific law. So we're saying that thing can be repeated over and over again, and it will always be 0.0003 gram. And they assume that people who are doing that in school with different people together, and they should all, apart where they did it a bit differently, the whole setup, come to the same result. Faraday's first law of electrolysis states that the mass of a substance liberated during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. There we have it. There has someone written, Richard Faraday has written a law to that it's always the same. And all we should do is find out if it was true. So, Faraday's first law of electrolysis states that the mass of a substance liberated during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. The mass of a substance liberated by one coulomb of electricity is called the electrochemical equivalent of a substance, where we have the title electrochemical equivalent. But the word makes some sense. It's the electro and it's equivalent in the chemical thing. So one coulomb is in its chemical element equivalent with the ability to transport it of 0.00033. Arising from our experiment, it can be stated that the electrochemical equivalent of copper is 0.00033 gram per coulomb. Electrochemical equivalents: copper 0.00033, silver 0.001118, and nickel 0.00031, oxygen 0.0000829, hydrogen 0.0000104, and chlorine 0.00037. Now, this were not telephone numbers. This was the end of our electrical engineering part. This was how much one coulomb of current can transport of a chemical element, or listed these different ones. It was the electrical engineering part. If you are here for electrical engineering, you can go directly to the next part of electrical engineering, where we will continue with the next thing in electrical engineering. If you stay here and participate in the shortened, we have just 2 minutes, stay in yoga, and it's at your own risk. Then we feet stand together, and we're breathing in and lifting the arms up. And breathe out the arms again down. In and the arms up. Out and down. In and up. Und on the other side. In and up. Out on the other side. In and up. Make an inch of space between the feet and out again to one side. In and cover out to the toes. And breathe out and go down a bit. This can go a bit underneath. In and up, reach high. Out onto the other side, heels again down. In and up onto the toes. And out and down. In, up. And out and down, feet again together. Breathe in, bend the right leg. And breathe out and stretch your left leg. In and change. Out, stretch your left leg. In and change. Out the right one. In and change. And one more time. One more time. And now breathe in, lift your right hand up to the sky. Bend the left knee and look over the right shoulder to the right hand. Inhale down. Out and down. Breathe in, lift the left hand up to the sky. Bend the right knee and look over the left shoulder to the left hand. Inhale down. Out and down. Now make a hand of space between the feet. Shift weight to the heels. Breathe in and go down. And out and up again. In and down. Out and up. Take out on the elbows and gently rock from side to side. Hands again down, feet together. Breathe in, come halfway up with a straight back. Out and down. In, halfway up, straight back. Out and down. In, up again. And lean back and draw the shoulder blades together. Breathe in, over, cross the arms into 20 fingers. Breathe in, reach high. Breathe out, reach in front, hollow back. In and up. Intertwine the other way around. Breathe in, reach high. Breathe out, reach in front, hollow back. In and up. Out, lean with long arms back. In and up. Out and back. In and up. Out and down. Bring the arms up. Bring the hands to touch and lower the hands down for heart center. It was a short stand yoga. I thank you very much and until next time.